Today we're diving into something that's way more than just a dental procedure. We're actually exploring this incredible story of medical innovation, where scientists are figuring out how to convince the human body to literally rebuild itself from the ground up.
I mean, just think about that for a second. What if you could regrow bone, ligament, and tissue that was lost to disease? It sounds like something straight out of science fiction, right? But it's the reality of a field called periodontal regeneration. So let's break down how it all works.
So why do we even need this incredible technology in the first place? Well, it all starts with a very specific and often totally hidden problem in your gums. One that can have some really serious consequences for your health.
It's called a residual periodontal pocket. The easiest way to think about it is like this tiny, deep space that forms between your gum and your tooth. And it sticks around even after the initial cleaning and treatment. It becomes the perfect hideout for harmful bacteria. And that's where the real trouble begins.
Now, in the clinic, there's a magic number everyone's watching for: 6 millimeters. As soon as a pocket gets that deep, it officially enters the danger zone. Why? Because it becomes pretty much impossible to clean properly, turning it into this chronic source of infection and inflammation.
And the stakes here are really high. These deep pockets are a huge red flag that gum disease, or periodontitis, is getting worse. And they are strongly linked to the ultimate consequence: losing the tooth completely. The bottom line is, these pockets have to be dealt with.
But how do you fix it? This is where things get really interesting, because we have to make a critical distinction. The goal isn't just to patch up the problem. No, the ambition is so much higher than that. We're talking about a full rebuild. And this brings us to the key difference between repair and regeneration. Repair, that's basically just a patch job. It seals the area, sure, but it doesn't bring back the original complex structure. Regeneration, on the other hand, is the whole shebang. It's the complete rebuilding of everything that was lost. New bone, new ligament, a new tooth surface, all of it working in perfect harmony again. That is the holy grail.
You might be thinking, okay, but our bodies are pretty great at healing themselves, right? Why is this so difficult? Well, it turns out that achieving true regeneration means overcoming some major biological hurdles. It's basically a race against time, happening in a very, very tough environment.
There are 4 big ones. First off, the fast-growing soft tissue, the gums, loves to rush in and fill the empty space. It gets in the way before the slower-growing bone and ligament even have a chance to get started. Second, the workspace is microscopic. Third, the root surface itself has zero blood supply to help with healing. And finally, you have to somehow coordinate the growth of 3 completely different tissues all at the same time. It's an incredibly complex biological construction project.
So how on earth do clinicians get past all these challenges? Well, they've got this amazing toolkit of what are called biomaterials. They're designed to guide the body's own healing powers and, really, to give those slow-growing tissues a fighting chance.
And in this toolkit, you've basically got 2 main players. On one side, you have bone grafts. These are actual living tissues that contain bone-forming cells. Think of them like bringing a whole construction crew to the job site. On the other side, you have bone substitutes. These are non-living scaffolds. They provide the framework, but they have to rely on the body to bring in the workers.
Okay, now we're getting to the really cool part, the core science. See, these materials don't just sit there and fill a space. They actively communicate with the body. They work through 3 key mechanisms to kickstart that entire rebuilding process.
The first mechanism is called osteoconduction. The best way to picture this is like a trellis for a climbing plant. The material just provides a passive scaffold, a physical framework that the body's own bone-building cells can crawl along and start building new bone on top of. It's that simple.
The second one is much more active. It's called osteoinduction. This is like a foreman on a construction site, actively shouting out orders and recruiting local, undecided cells to become dedicated bone builders. The material actually releases signals that switch on the body's own regenerative machinery.
And the third and most direct method is osteogenesis. This is like rolling up to the site with a prefabricated unit ready to go. The graft material itself has living cells inside it that are ready to start building new bone immediately.
And here's how it all comes together. Simpler materials like calcium phosphate are just conductive. They're only the scaffold. More advanced ones, like processed donor bone called DFDBA, are inductive. They act like that foreman. But the gold standard?
That's an autogenous graft, one taken from the patient's own body. It's fully osteogenic, which means it has all three properties: the scaffold, the foreman, and the prefab crew.
So in a perfect world, what would the ideal off-the-shelf material actually look like? Well, researchers have a pretty clear checklist, a kind of wish list that they're all working towards.
Here's that wish list. First, you'd want an unlimited supply and for it to be totally biocompatible, so the body doesn't reject it. You'd want it to encourage new blood vessels to grow, which is a huge deal for healing. Critically, it would have to be both inductive and osteogenic, so it's providing both the signals and the cells. And finally, you'd want it to slowly dissolve away at just the right speed, being perfectly replaced by the patient's own healthy new bone, and let me tell you, that is an incredibly difficult balancing act to get right.
But it's so important to remember the real goal here. It's not just about filling a hole with bone. This whole field represents a revolutionary shift from just managing a disease to actually reversing the damage it caused. True success means flawlessly recreating a complex, living system, that entire attachment apparatus that holds a tooth firmly and healthily right where it belongs.
And that leaves us with a really fascinating thought. The lessons we're learning from rebuilding these tiny, complex structures in the mouth are pushing the absolute boundaries of what's possible in medicine. And it just makes you wonder, right? If we can do this here, what other parts of the human body are we going to learn how to regrow next?